All right, well, let's start today with a warm-up. Well, of course, by the time we get to the end, you'll say, boy, that's the warm-up? Yeah, this one's a little bit more fun than most. But all right. Find the limit as z goes to 0 of, then you have this expression, 1/2 e to the 2z minus sine of z plus 1/2 cosine of 2z, and all of that is being raised to the power 1 over z cubed. All right. Now, first impressions are, what do we do? Now, I'll tell you that there's actually a really good clue on what to do. It's right here. The fact that this is a limit. Now, in this part of the course, the only time we ever talk about the word limit is when we did what? When we did le hôpital. Oh, le hôpital. Okay, so if you see a limit, you should be thinking, I wonder if this is a le hôpital problem. Well, let's find out. Now, the first thing you should always do is you should say, well, what happens if z were to be 0? So let's see what this is going to. So currently, well, that's 1/2 e to the 0, which is 1/2. Sine of 0 is 0. Cosine of 0 is 1, but then times 1/2, so that's 1/2. So upstairs, it's looking like it's going to 1 over 0. Now, if you look at it, really this is like 1 to the infinity. Because the inside part is going to 1. The exponent is 1 over a very tiny number, which is a big number. So it looks like 1 to the infinity. And 1 to the infinity means what? More work. It's one of our indeterminate forms. Now, are we able to apply L'Hopital right away? No, because we can only apply L'Hopital once we get a fraction. We have to have something over something. It has to go to 0 over 0 or infinity over infinity. So you might say, I know how to get a fraction. I just put it over 1 and then I have a fraction, right? No, it's more than that. It has to be a fraction going to 0 over 0 and infinity and over infinity. One of those two. That's it. So how do we proceed? Well, the problem is that exponent. We want to bring the exponent down. So how do you take something from the exponent and bring it down? You use the logs. So the key here, there's only a handful of things you do when you have indeterminate forms. If it's not already a fraction, you use logs to bring down the exponents, or you do some simplification to get it as a fraction or fraction like conjugation, things like that. So logs is a very common thing. So let's, for a second, we call L whatever our limit will turn out to be. We don't know what it is yet, but we're going to find it because we're persistent. All right, now what do we do? Well, we're going to take the log of both sides. So the log of L, and here's the nice thing. So it looks like I take the log of the limit. But because log is a nice function, and by nice we mean continuous, I can push log into the limit. So this is the same as the limit as z goes to 0 of log of everything. And now we say, okay, we knew we did log for a reason because we are now going to bring that exponent 1 over z cubed is going to come down. And in fact, it's going to come down really quick because it's 1 over z cubed. That would end up being a z cubed downstairs. So this is the limit as z goes to 0 of natural log 1/2 e to the 2z minus sine of z plus 1/2 cosine of 2z over z cubed. Now, this is going to, upstairs, log of 1, which is 0, downstairs, 0. So what can we do? L'Hopital. Now, before we start, we can kind of predict where this problem is going to go. How many times do you think we're going to have to do L'Hopital? Probably a bunch of times, because that's a cube. It's going to take a bunch of times to drive it down, which is good. We need our practice with derivatives. So Here we go. L'Hôpital number 1. Hello, L'Hôpital. How are you? Limit as z goes to 0. All right. And remember, this is not a quotient rule. So you're taking the derivative of the top over the derivative of the bottom. So the derivative of natural log, that's 1 over the inside, 1/2 e to the 2z, minus sine z, plus 1/2 cosine of 2z. And then we're going to multiply that by the derivative of the inside. Well, derivative of the inside, derivative of 1/2 e to the 2z, e to the 2z. So e to the 2z. Derivative of sine z is cosine z. 1/2 cosine 2z will be negative sine of 2z. All right, good. And that's being divided by 3z squared, because it's the derivative of z cubed. Now, I'm going to rewrite this. Limit as z goes to 0. So upstairs, e to the 2z minus cosine of z minus sine of 2z. Whoops. Sine of 2z, all divided by 3z squared times this other stuff. I'm just going to write as 3z squared times this other stuff. I'm not going to multiply it out. I don't have to. It's not a requirement. Okay. So what do we do next? Well, what happens when we try to go to 0? Downstairs is pretty easy because you have that z. That's going to knock everything out. How about upstairs? What do you get? First term will be 1. Second term will be negative 1. Last term is 0, which is 0 over 0. Aha! So what do we get to do? We get to do more work. Wow, we're lucky people. Okay. So we get to do L'Hôpital again. Nice. Limit as z goes to 0 of derivative upstairs, 2e to the 2z. Derivative of negative cosine z is plus sine of z. Derivative of negative sine of 2z will be minus 2 cosine of 2z. And then downstairs, we'll get, derivative of 3z squared is 6z times this other part, 1/2 e to the 2z minus sine z plus 1/2 cosine of 2z. And then plus 3z squared times this derivative. Well, that's not so bad. We actually took the derivative before. It's e to the 2z minus cosine of z minus sine of 2z. All right. So, what happens to that? Well, we plug in 0. And if we plug in 0, downstairs, that z and that z squared, that's going to knock everything out. So the denominator is 0. What happens to the numerator? What do we get? Well, you're going to get 2 plus 0 minus 2, which is 0. 0 over 0. So what does that mean? More work, right? Good. Just when we thought we were going to be done with our work, it pulls us back in. All right. So, this equals, keep going here, L'Hôpital, limit as z goes to 0. All right, what's the derivative upstairs? 4e 2z plus cosine z. Okay. Then plus 4 sine 2z. All over. Okay. A lot of stuff. Derivative here is going to be 6. Derivative of 6z is 6. Then this piece here. And now, at this point, you're probably thinking he's not going to have enough space on his page. And you're right. Plus z times stuff. Okay, in the interest of time. In the interest of time. Now, it turns out it's not very hard to take this derivative. you'd have 6z times that derivative plus another 6z times this, so you could combine them together. So the stuff, in case you're wondering, for those people who really want to know what is the stuff, this is what the stuff turns out to be. 12z, 1/2 e to the 2z minus sine z plus 1/2 cosine of 2z. And then plus 3z squared times 2e to the 2z plus sine of z minus 2 cosine 2z. That's what the stuff turns out to be, but I'm not too worried about that, because I know there's a z attached to everything else after that. Now, what happens upstairs? What do you get? Well, 4 plus 1 plus 0, which means game over. Whatever happens, it's about to happen now. 5. What happens downstairs? Well, the z times the stuff, because z is 0, it's going to knock out all of that. Okay, so that's gone. The 6 is the 6. How about that part? Well, it's 1/2 minus 0 plus 1/2, which gives us 6. So, is 5, 6 our answer? No. No. Good. You've learned the way. Never trust him when he asks the question. Why? Because remember, the log of our answer is what we were finding. So the log of our answer is 5, 6. So what's our answer? We've got to get rid of the natural log. So what gets rid of the natural log is e. So e to the 5, 6. Probably not what you would have guessed. But you don't have to guess, because we have better tools. All right. This is clearly, by the way, more challenging than anything we'd give you on an exam. But it's a lot of fun to do these ones, because it really helps us stretch ourselves. We like to be challenged. So today, and also next time, we're all going to be talking about one thing: optimization. So optimization is a really important thing in calculus. And so the goal of optimization says, I'm after the best. So what does that mean? Well, it depends on the context. So you might have something with the most area, or the least volume, or the tallest thing, or the shortest thing. You want the most amount of money. You want the least amount of cost. Oftentimes, the thing is that we have limited resources. We want to say, how can we get as much as we can out of those resources? That's what optimization is about. So, what do we do? How do we approach these problems? Well, we've already kind of learned how to approach these problems, because when we're trying to find the most of something, it's like we're trying to find when things are maximal or minimal. So we've learned how to find maximums and mins. We know that these happen at critical points, and we know how to classify things as being max or mins. So now we have sort of a plan. We say, okay, if we're trying to optimize something, write it, if we can, as a function of a single variable, and look for critical points. And then we test them and see, okay, is this what we're looking for? Oftentimes we can use context to figure out what's happening, but we can also go further and apply tests as needed. Now there's this word of warning here: check if your answer is reasonable. Well, what does that mean? I've had problems in the past where I would have a problem which involved, find the height of a mountain. And I've had students write down, without even casually thinking about it, this mountain is 20,000 miles high. Now, that's pretty impressive considering Everest is somewhere around 6. So 20,000 is amazing. But they didn't even think to say, hey, that doesn't make any sense. So you should always sort of say, does your final answer make sense? Is it intuitively, is it something that's reasonable? If it's not reasonable, you should check your work. It could be that there's something amazing happening. I don't want to rule that out. But you should always be suspicious if things are very unreasonable. For instance, if you're trying to maximize area and your final answer is a negative number, that's an unreasonable thing. All right, so what's the procedure? It's very simple. The first thing is you have to understand what's being asked. What's the problem? What is it we're trying to optimize? What can we vary? What's allowed to change? And do we have additional relationships? Because sometimes we might have several things involved, but perhaps they're related to one another. And the relationships are useful if we have multiple things because we can condense things down to a single variable. Now, step 2 says, if you need, draw a picture. Now, not everything has a picture attached to it, but we're very geometrical. We like to sort of see things. And many of the problems are expressed in geometrical terms. You know, it's like we're looking for a box with certain properties. Okay, draw the box. What does it look like? The real important thing here is number 3. Figure out what is it you're trying to optimize and express it as a function of one variable. And once you've done that, you're like 80% of the way there. Because now you say, I have my tools. And my tools are, I find the critical points using derivatives. I classify them as I need. If there's endpoints, I check the endpoints. And then I'm done, and I just make sure I give the answer. So pay attention to what's being asked. Sometimes you may want to say, what are the parameters? Sometimes you're going to say, what is the output? So just pay attention to what's being asked. And so most of these are really nothing new. It's just we're adding on an extra layer of words. And so there's lots of word problems coming our way. So brace yourself. The English is coming. Okay. Let's begin. And we'll see how many we can get through. And don't worry, there's so many problems. We'll have more for next time. So the first one. Find the maximum area we can enclose using 400 feet of fencing in the shape of a rectangle where one side does not need any fence. For example, it might be being built next to a river or a cliff or some other object which acts as a natural barrier. So what do we have? Well, let's suppose we have a river, and I'm going to draw a river here. And you can tell this is a river because of how good my drawing is. You're convinced once you see it, you just look at it and you think, yeah, river, right there. Now, what's our shape? Well, we're looking for one side of a rectangle is against the river. So we're probably thinking something like this. Now, of course, there's many possibilities, but it's very unlikely that we would build something that looks like that, because that just does not seem to be efficient. Somehow you want to use advantage of the river being there. So I say, okay, so that's our basic setup. Now we need to start thinking about things. And in our picture, we think about things by saying, well, let's label things. We don't need to label the river. It's there. But in terms of a rectangle, what should you label on a rectangle? Yeah, you should label the sides of the rectangle. So what do we have? Well, we can have, say, X and Y. All right. So we'll label those sides. Now, what do we know? Well, we're trying to maximize what? We're trying to maximize area. So we want to maximize X times Y. Now there's a problem here. We have two variables. This is not multivariable calculus. That's next year. We want single variable calculus, so we've got to get down to single variable. So we have to use additional information because we haven't used everything. See, it says 400 feet of fencing. Okay, so what does that mean? There's 400 feet if we go around here. So if we add up X and Y, or maybe I'll say X plus Y plus X, that's the total amount of fencing. That's 400. So this is the relationship between X and Y. We can already use that fact that we're looking for X times Y and say, well, let's solve for one of our variables. Which one should we solve for? Well, I'm asking you the question about which one we should solve for because, you want to solve for the variable Y. Okay, I'm sorry. Okay, Y equals 400 minus 2X. And so we can put it in here and we say, okay, now we have our area function is X times 400 minus 2X. Notice one variable. So let's call this area as a function of X. And if we're going to take a derivative, it'd probably be best if we first multiply this out. 400x minus 2x squared. So now we take our derivative because we're looking for our critical points. So what is our derivative? Well, derivative of 400x minus 2x squared. 400 minus 4x. And we set this equal to 0. What does that say about x? It says x should be 100. Now, if x is 100, what should y be?
300.
Well, 400 minus 2 times 100. So x should be 100, and y should be 200. That's what we think. Now, in some sense, you can say, look, I'm after a maximum, and that should be it. We should ask, is that truly optimal? Now, because there are some extremes, and there's a natural constraint here. What's true about x? It's not just that we have this area function. X can't be arbitrary. Where can x go between? 0, because we can't have negative lengths. What's the longest? The longest we could have is 200. So we can either use geometrical intuition to rule this out, or we can use some other test. So geometrical intuition says if x were, say, 0, that would say put your fence up alongside the river. Well, how much area is there? There's no area. It's terrible, terrible. Wouldn't do that. If x were 200, it would say take your fence, go out 200, and then put it right back. It might work for, modern art, but not very useful otherwise. So at the extremes, the area is 0. And therefore, we know the max can't happen at the endpoints. So it has to happen somewhere in the middle. So that's an argument that 100 is a max. Another argument you could give is we could do something like a second derivative test. What is a double prime of x? Negative 4. Now, what does that tell me? Well, that tells me at my critical point, which is 100, what is a double prime? Negative 4. That's actually always negative 4, which is concave down. If I'm concave down, what does that tell me about my critical point? It's a max. So that's a way to check if something is a max. Use a derivative test, so a first derivative test or a second derivative test, or use the geometrical reasoning saying, okay, it can't be at the endpoints because you would get 0 out, and 0 can't be the right answer. All right, well, you are doing a final study session before the quiz. Ooh, applied math, this is good. The longer that you study, the more you will know, but you will also be more tired. After some thought, you come to the conclusion that if you study h hours, your score on the quiz will be 11.2 minus 5 over h plus 1 minus 0.8 times h. How many hours should you study for the quiz, and what will be your score? All right. Now you're probably thinking, okay, how do I draw a picture? Not all problems have to have a picture. What do we need, though? We need a function. How do we find a function? The answer is we point to it. It's right there. I found it. Okay. So that can happen. So in this case, this is a nice problem in that they're giving you the relationship that you're after. So we're trying to optimize this function. So let's give it a name. So this will be a function, and I'll call it f as a function of h, because here, our variable, the thing that's being changed, is h. Now, we do what we would do in any situation. We take ourselves a derivative. What is f prime of h? So, derivative of 11.2? 0. Derivative of 5 over h plus 1. Now, that one, we could help ourselves by saying, let's rewrite it. That's h plus 1 to the negative 1. So if you write it in that way, it might be easier to take a derivative. So what's the derivative of negative 5 times h plus 1 to the negative 1? Well, the negative 1 comes down. So it'll be positive 5. H plus 1 to what power? Negative 2. Then you multiply by the derivative of the inside, which is 1. Subtract 0.8. All right. Now that's our derivative. We're looking for our critical points. Now, there is a critical point at -1, but we don't count that because it doesn't make any sense for our problem. We can't study for -1 hours. It's not like we were going to be like, I studied too much calculus. Let me go watch some reality TV. That'll cancel it out. So we're going to assume that h is always greater than or equal to 0. So okay, so we don't have any points where the derivative is undefined where we care about. So what do we care about then? Well, what kind of other critical point can we have? We could have it where the derivative is 0. So we're going to set this equal to 0. So what do we have? Well, this is 5 over h plus 1 squared is equal to, because I'm going to bring that across, that's 0.8. And let's put that back into a fraction. Let's make that 4/5. So 0.8 is 4/5. If we rearrange, well, let's actually just flip both sides over. How about that? H plus 1 squared over 5 is equal to 5 over 4. H plus 1 squared is equal to 25 over 4. Now what? Well, take the square root of both sides. We'll get h plus 1 should be 5 over 2 plus or minus. But some of these we can rule out. So for instance, here, if we said h equals -1 plus or minus 5 over 2, again, a minus and minus on top of that is not going to work because we need to have hours has to be at least 0. We can't have negative study time. So that says the only critical point is at -1 plus 5 over 2. Or if you like, if you were to simplify that, that would be 3/2. About 1.5 hours. On a side note, my help hours last about 1.5 hours. Maybe that's a good sign. We're doing the right amount of studying if you go to help hours. Okay, now let's not get distracted. Is this a max? Can we figure that out? What can we do to test? We can do a second derivative test. Second derivative test is not so bad. How about f double prime of h? What does that turn out to be? Well, the negative 0.8 goes away. It becomes -10, h plus 1 to the -3. If we plug in 3/2, what will we get? Again, we only care about the sign. Plug in positive 3/2 into this expression, we end up with negative value. So f double prime of 3/2 is negative, so 3/2 is a max. We could also do the first derivative test and say, well, here's 3/2. If you plug in 0 into your first derivative, you're going to get 5 minus 0.8, which says that your first derivative here is positive. If you plug in 1,000,000, then this term is negligible, goes away, and minus 0.8 means that it's going to be negative over here. So you're going up, then down, which means 3/2 is a max. You don't have to do both tests, but you should be ready to do one of the tests to do your justification. Not all questions ask for justification, but I want you to be ready for it in case it does. Okay, so our final answer is we should study for 1.5 hours. And what will be our score? I hope it's a good one. Let's find out. So we plug in f of 3/2. So that's 11.2 minus 5 over 1 plus 3/2, whatever that turns out to be, minus 0.8 times 3/2. Well, it's not so bad as it might look. 0.8 times 3/2. If I take 0.8 divided by 2, that's 0.4. 0.4 times 3 would be 1.2. This is 11.2. So that's really If I combine the 11.2 in this last term, that's 10. Then here, 1 plus 3 halves is 5 halves. So it's 5 divided by 5 halves. You flip the 5 halves over, that will become a 2. 10 minus 2. So our score will be an 8. That's a decent score, a good score. They're pretty strict on grading, so a score of 8, not too bad. Okay. Now, another common problem that vexes many of us. You've discovered a discount store selling sweets in Diagon Alley. You decide to make a large purchase and ship 15 pounds of candy back to your school. The chocolate frogs, which we denote F, each weigh 4 ounces. And the Birdie Bots every flavor beans, denoted B, come in 12 ounces bags. This probably should be 12 ounce bags, but okay. After some thought, you decide that your happiness about the purchase is measured by the function b to the 2/3 times f. How much of each sweet should you purchase to maximize your happiness? Okay, good. Well, we're always about maximizing happiness, so this is a positive sign. So, in some sense, we know what we have to maximize. We have this nice function here. So our goal is we want to maximize b to the 2/3 times f. What's our challenge right now? There's 2 variables, which is too many. So we say, okay, we need to get rid of one of the variables, which means we're looking for a relationship. Now there's a couple of key words here. There's the 15 pounds. So that tells us that whenever I see a number, I think, okay, that's a limitation. So the chocolate frogs weigh 4 ounces, and the Birdie Bots every flavor beans weigh 12 ounces. Okay. So let's think about what's true. Now, we have to think about 15 pounds and ounces. This needs to know a little bit about how ounces and pounds relate. How many ounces are in 1 pound? 16. So, okay, so that's good to know. So, for every frog, I'm using up 1/4 of a pound. So the total weight of the frogs is 1/4 F. So I'm measuring my total weight in pounds. The total weight of the beans, well, how much would that be? 3/4 times the beans, and that would give me my 15 pounds. Now, I don't like fractions, so I'm going to go ahead and just immediately multiply everything by 4. So however many frogs I buy, plus 3 times however many Birdie Bots, I'm going to get 60. Okay, so that's the limitation. So that's the relationship between F and B. Now, at this time, we should solve for one of those two. Should we solve for F in terms of B or B in terms of F? Now, you might say, does it make a difference to the answer? And it will not. So, if it doesn't make a difference to the answer, you should say, solve for the one that's easiest. And there's 2 things that suggest that F would be easier. If you solve for F here, you don't have to introduce fractions. If you solve for B, you'd have to divide by 3. That means fractions. And if it's one thing I've learned, fractions can challenge us. There's something else. Notice that in our function, B is raised to the 2/3 power, but F isn't. So it's simpler if we substitute for F. So we have that F is equal to 60 minus 3 times B. And we're going to make that substitution into our expression. So what we're trying to maximize now is B to the 2/3 times 60 minus 3 times B, which is, if we multiply the B to the 2/3 through, 60 times B to the 2/3 minus 3, then I have B times B to the 2/3, which becomes B to the what power? 5/3. Okay, so here's our function. I'll call it H for happiness. Happiness based on how many of the beans we buy. So, what comes next? Take a derivative. So we have our function now down to a single variable. We take our derivative. H prime of B, what will that become? Well, 60 times 2/3 b to the negative 1/3, then minus 5/3 b to the 2/3. Sorry, what? Oh, you're right, there's a 3 here. I forgot. Okay, back on track. Good to check your work. Okay, 62 times 2/3 will give us 40, because 60 divided by 3 is 20. B to the minus 1/3, and then the 3's cancel, so minus 5. B to the 2/3, and here probably the easiest thing is let's pull out a 5. B to the negative 1/3 power, and if we do, the first term we're left with 8 minus, and the second term we're left with b. So what are the critical points? Well, there is a critical point at 0. Now, b equals 0 will not be our max. How do we know that? How much happiness will we experience if we buy no beans? 0 happiness. So we need some frogs in our life. Okay, the other critical point is b equals 8, which means there's only one critical point. It's got to be our max. So definitely our answer is going to be 8 of the birdie bots. And how many frogs are we going to have? Well, we can substitute b equals 8 into this expression. 60 minus 24 gives us 36 of our frogs. Now, if we did want to check, we could do, for instance, a first derivative test. We could say 8. If you plug in a number below 8, you'll see that our derivative, say 1, is positive, and that's positive, so we're going up. If you plug a number after 8, say 1,000,000, not that you can purchase 1,000,000 of your birdie bots, but okay, doesn't matter. Just pick a number, you'll see it's negative. So it is indeed a max. All right, good. Let's do a geometry one. Okay, let's see, do we have enough time? 15 minutes, we might be able to finish this one. Find the area of the largest triangle that can be inscribed in the unit circle with one vertex at 1, 0, and the opposite side parallel to the y-axis. So let's draw the picture so we understand. The unit circle is our circle radius 1. So let's pretend that's the circle. Here is the vertex 1, 0. And now what we have is that's one vertex. The opposite side is going to run straight up and down. So see, it's parallel to the y-axis, so it's running straight up and down. So it could be there, or it could be there. It's probably not going to be there. It's probably going to be on the other side. So it's going to be somewhere here. So let's say this is our other side, and now we have a nice little triangle. And what do we want? Well, we want to find the area of that largest triangle. Okay. So we're after area. Okay. Sounds good. So if we're after area, let's start thinking about how we can find area. How do you find area of a triangle? We can do base times height. And notice that we can think of it, if we sort of turn the picture momentarily sideways, we can think of this as our base, and this is our height. It's probably easier to think of it that way than to try to, like, well, what's the base at? So think of this as base, and that's height. We'll multiply by base height, then divide by 2. So we need to have something that's varying. So one of the things we can think of is I can think of, let's think about this point, because I can move that point to various places. You know, I can move it over here, and I get a very skinny triangle. I can move it way up here, and I get a very fat triangle, but it's a little bit shorter. So you're sort of trying to balance those two. As you move the point around, one side changes to your favor, but the other side changes against you. So it's either one side's getting shorter, but the other side's getting longer, and vice versa. So it's like trying to balance those different demands. That's why you have optimization. You have to balance those two different conflicting things. So let's think about how we can describe it. So I think probably the easiest thing is to think about this as a point. Suppose I say the x-coordinate is x. Very, very imaginative, I know. Now you're probably thinking, what's the y-coordinate? Well, y, that would work, but we'd really want to get it down to be in terms of x, because if we can get everything in terms of x, life is great. So we know we're on the unit circle. What's true about points in the unit circle? X squared plus y squared is 1, because I'm on the unit circle. Unit circle means radius 1. So the y-coordinate I can actually solve. And I can say, well, y squared would be 1 minus x squared. So y would be plus or minus the square root of 1 minus x squared. The plus is the top half. The minus is the bottom half. I'll just worry about being on the top half, because I can think about this sort of top point moving around. So I get the square root of 1 minus x squared. And in particular, we can see that x is going to go from negative 1 up to positive 1. I can't go beyond that, because that's where my unit circle lies. And that's forced upon us because of the square root of 1 minus x squared. Now we need to figure out the area. So our area as a function of x is 1/2. Now we have the base. So the base is this side here. So what's that length? Spoiler, it's twice that length.
2x.
So it'll be 2y. It's the y value. So 2 square root 1 minus x squared. Now, what's the height? This distance. Well, over here I'm at 1. Over here I'm at x. How far apart are these? They're 1 minus x. And there we go. So, there's our expression. We just have to optimize that, and life is good. Now, there's a couple of things we can do. Well, one really easy thing we can do is we can cancel off the 2's. That's good. I'm debating about whether or not to do the next thing. There's two routes to go down, which is just to say, let's work with this as is. Okay, there's three options. We can say, keep it as is. So area of x would be the square root of 1 minus x squared times 1 minus x. Another option is to say, hey, wait a second. 1 minus x squared, what does that turn out to be? It's 1 minus x, 1 plus x. And the reason that we might notice this is also 1 minus x. So this is 1 minus x to the power 3/2 times 1 plus x to the power 1/2. That's one option. And then the third option says, oh man, do I got to work with the square root? And the answer is, no, you don't have to. You can actually save yourself a little bit and say, you know what, instead of optimizing area, I'll optimize this function. I'll call it area of x squared. I'll call it b of x. And this function is the function 1 minus x squared times 1 minus x squared. Of course, when I say it out loud, you didn't hear my parentheses, so that's not quite the same. So the nice thing is, if I want to optimize area, it's equivalent to optimizing the square of the area, because area, it's a non-negative measurement. So to make it as large as possible, I just have to make the square as large as possible, and that helps us avoid having to deal with the square root. So which root would you like to take?
Third.
Should we try the third one? See where it takes us? I'm not claiming it's easier. I'm just saying it's an option. If I were going to take this route, I probably would multiply it out because I'm foolish, and I do foolish things. So 1 minus 2x plus x squared times 1 minus x squared, which would become 1. So I'm just going to multiply the 1 through. So 1 minus 2x plus x squared, and multiply the minus x squared through. So that would be minus x squared minus 2x cubed, plus 2x cubed minus x to the fourth. And you can clean this up ever so slightly. You might notice that you have an x squared and a minus x squared. They will end up canceling. So you have 1 minus 2x plus 2x cubed minus x to the fourth. And now, that's it. That's the simplification. Now what do we do? Take the derivative. Okay, so that's what we're trying to optimize. So we take the derivative. What do we get when we take this derivative? Negative 2 plus 6x squared and minus 4x to the third. Okay, cool. Nice. Now what? Well, we're looking for critical points, right? So how do we start looking for critical points? Well, we should try to factor that. So what can we do? We can pull out a negative 2. That's easy to do. And let's just pull out a negative 2 and rewrite it. That's 2x cubed minus 3x squared plus 1. All right, now what? Now you're like, I regret our choices. No. It was always a wonderful idea to take calculus. So, when you get to a point like this, one of the things you start thinking about is, how could I factor? Well, let me just try a couple of roots. So, is 0 a root? No, if 0 was a root, we couldn't have a constant term. So what's the next number you should try? 1. You should always try 1 because it's so easy to try 1 that it takes almost 0 effort. How do you know if 1 is a root? What do you do? Well, you plug it in, but the nice thing is 1 to any power is always 1, so you add up the numbers. Do these numbers add up to 0?
Yes.
Yes. That means 1 is a root. So, running out of space. This becomes negative 2. Because 1 is a root, x minus 1 has to be a factor. By the way, we know the answer is not going to be 1. How do we know that the answer is not going to be 1? Well, if you put in x equals 1, you get a triangle which is a single point. Not very much area. Okay, so that's not going to be our max. Then you have this other stuff. Now the other stuff, you can figure out parts of it pretty quick. X times what gives me 2x cubed? 2x squared. Negative 1 times what gives me 1? Negative 1. So I need negative 1 times negative 1 to give me positive 1. And now we start thinking to ourselves, okay, how do we get to 3x squared? Well, we're going to get minus 2x squared from there. And then we need to get another something to end up with a minus 3x squared. The only way that will work is if this is a minus x. Because I have a minus 2x squared already. So I need a minus x squared to get to minus 3x squared. And you can check it works out. Now, 2x squared minus x minus 1, does that factor? Well, is 1 a root? It's still a root. 2 minus 1 is still 0. What's the last piece? 2x plus 1. So we get two candidates, x equals 1, which is not going to work. X equals negative 1, for the same reason, is not going to work. So what's the only candidate left? X equals negative 1/2. Now, is that our answer?
No.
It's not the answer. What do we need to find? What's our final answer going to consist of? It's going to be an area. So whatever our answer is, it has to be an area. What we found is where to put that other opposite side. So to get our final answer, as we plug in this negative 1/2 into our original function. So we get the square root of 1 minus 1/4 times 1 minus minus 1/2. So that would be the square root of 3/4, which is the square root of 3 over 2, times 1/2, 3/2, 1 plus 1/2. And so our final answer is 3 square root of 3 over 4. That is the maximal area. All right, so let's suppose you didn't want to square this because maybe you didn't think about it, or maybe you're not comfortable with it. Now, it's perfectly fine to keep squaring it and to work it out. But it's also perfectly fine to not do it. So suppose that you didn't have anything insightful, and you just said, okay, I see square root of 1 minus x squared times 1 minus x. That's what I'm optimizing, and I'm going for it. So let's see if we still get the same answer. And so we'll write it down. A of x is the square root 1 minus x squared times 1 minus x. Now, of course, we will do the very calculus thing of saying this is 1 minus x squared to the 1/2 times 1 minus x. Take our derivative. A prime of x is, now we do our product rule. Derivative of the first, 1/2, 1 minus x squared to the minus 1/2 times the derivative of the inside, which is minus 2x. Keep the second function the same, 1 minus x. Then we add to that 1 minus x squared to 1/2, which is the first function, times the derivative of the second function, which is negative 1. Here we say, okay, what can we do? Well, some things we can do pretty easily is that we can cancel the 2's. Farewell 2's. Okay, so that's good. What else can we do fairly easily? Well, we can also factor things out. So what do they have in common? Well, they both actually have a minus sign in common. Well, that's interesting. And they both have 1 minus x squared in common. So I'm going to factor out negative 1 minus x squared to the negative 1/2. And let's see what's left. So we got the negative. We got the 1 minus x squared to the negative 1/2. So we're left with x times 1 minus x. From the second term, we got the negative, and when we pull that 1 minus x squared to the negative 1/2, which means we're left with 1 minus x squared to the positive 1, 1/2 minus minus 1/2. All right, so this is negative 1 minus x squared minus 1/2, and then here we'll have x minus x squared plus 1 minus x squared. Well, maybe we shouldn't have pulled the negative out. So if we put the negative back in and relook at this, 1 minus x squared to the minus 1/2, negative x squared is negative 2x squared times the negative makes it positive 2x squared, then minus x minus 1, and we're back to where we were before, 2x squared minus x minus 1. So we end up with 1 minus x squared to the minus 1/2, and then here, this still factors as 2x plus 1 times x minus 1. Now, how does this simplify? Well, it turns out that there's a couple critical points. Some of them are coming here, plus or minus 1, because we're getting a 0. You'll notice that this is also 1. It turns out that if you're very careful, the reason that 1 is a critical point is because it turns out it's 0 if you were to combine these two. But definitely there's an issue with 1, and then we end up with negative 1/2. Well, we know our area can't be maximized at plus 1 or minus 1. See, at plus 1, our triangle would be a really boring thing. It would be just a single dot. That's it, right there. You see it? It's so tiny, you almost miss it. That's at x equals plus 1. At x equals negative 1, what's our triangle look like? Well, it's almost just as boring. It's a triangle that goes like that. You might call it a degenerate case, or an extreme case. It's a triangle where one of the sides has length 0. This is a triangle where 3 of the sides have length 0. But those both have area 0, and x equals negative 1/2. Well, that one's not so bad. we're over on this side where we should be, and we say, okay, that definitely, at least it has area, so that's got to be the right answer, whatever that turns out to be. All right, well, so again, you have options. You don't have to do things exactly as we do them. In fact, one of the things we hope you discover is that we're getting to the point in math where there's lots of different alternatives. So you should do what you're comfortable with, and that's the best thing for you. That's what you should be doing. Okay, let's do one more example. So 1,200 square centimeters, because that's what the 2 means, of material is available to make a rectangular box with a square base and an open top. So we have a rectangular box. So it looks something like this. Now it's a square base, which means that when you sketch this, we have this container here. All right. Square base means that these 2 sides are equal, and now an open top means that there's nothing here. There's no top side. But what do we have? Well, we have 4 sides, and then of course there is the bottom. Now, what we do is we say, okay, let's start to label stuff. How do we label stuff? Well, we want to label stuff in a useful way. So let's suppose we label this X. So again, because it's a square bottom, this will be X as well. X and X. And this other side, well, Y. Now there's nothing special about these X's and Y's. You could use L and H or W and H. We just are so used to using variable names as X and Y, so it's oftentimes easier for us because we're more comfortable. But comfort is not the only thing that we take in consideration when solving a math problem. So we want to find the largest possible volume. So the largest possible volume says, for a box, we want to multiply these 3 lengths together. So it'll be x squared times y. That's what we're after. The problem is 2 variables. So we want to reduce it to a single variable, which means I need to somehow get rid of either the x or the y. So looking at the picture here, we say, okay, what haven't we used? Well, there's nowhere we've written down 1,200. So that's what we haven't used. We've got to use that 1,200. So we have 1,200 square centimeters of material. So that's the part that goes into making the different sides. So we know that 1,200 is going to be, what happens when we add all the sides up? Well, we've got the bottom side, that's going to be x times x. That's x squared. Then we have 4 sides which are identical. They're all x by y. So there's 4 sides, and each one of them has area x, y. So there's 5 sides total, but remember, no top. So we need 1,200 equal x squared plus 4xy. So looking at this, we say, okay, what can we do? Well, we can substitute and solve for one of these variables. Let's go ahead and solve for y, because I can see here, if I were to solve for x, it would be a quadratic. And, well, that's not the best thing to do. Let's avoid that. So I could take 1,200 minus x squared. That's 4xy. And now I can say that y is 1,200 minus x squared. Divide that by 4 times x. So this, we're going to put into volume. So volume is going to be equal to x squared times 1,200 minus x squared over 4x. And here we can very conveniently multiply the x's together. Now you might want to say, well, wait, hold on. What if x were 0? Well, we have a problem. If x is 0, what does our box look like? Well, it looks like a little teeny tiny thing, and then this huge, almost infinitely long height. This is a bad box design. We don't want that because, well, first off, you can't put anything into it. There's just no volume on the inside. So definitely, look, x has to be greater than 0. So we're not going to worry about that case. So I can divide through, and so we really have here, this is 1/4 x times 1200 minus x squared. Multiply it through all the way. We'll get 300x minus 1/4 x cubed. So there's our volume. And I want to emphasize that this is a function of one variable, so I'll say volume as a function of x. You give me an x, that's how much volume we can produce. So we take our derivative, because we're looking for our critical points. That'll be 300 minus 3/4 x squared. Well, never undefined, set it equal to 0. 3/4 x squared had better equal 300. And now, what do we get? We'll multiply by 4/3, and we get that x squared should equal 400. 300 times 4/3, which says that x is 20. Now, of course, plus or minus 20, but we know x represents a measurement. It's the length of a side. Can't have a negative side. So, there we go. So we know x should be 20. Now let's just sort of check to see if this is reasonable. That would say that our box that we're constructing should be what? Well, it should be 20 by 20 by what? 1200 minus 20 squared. That's 1200 minus 400 would be 800. Okay. Then we're going to divide that by 80. And 800 divided by 80 is 10. So 20 by 20 by 10. So in fact, that's the wrong picture. It really is more sort of flat. Now, does that make sense? And the answer is yes. You see, we want it to be shorter. The reason we want it to be shorter is we can save money because there's not much material on this one side. So in essence, we really want this one side to be larger. So we should have a flatter box. A flatter box makes the top larger. Now, but again, the same constraint. If we make it too flat, then we're using a lot of space on that bottom side. Eventually, the trade-off doesn't work out in our favor. So it's finding that spot. Finding where does that trade-off happen. That's where optimization comes in. Now, that's not the area. Sorry, that's not the answer. What is the answer? Remember, the answer is a volume. But now we know. So the largest possible volume is going to be 20 by 20 by 10. Well, that's really 4 with 3 zeros after it. So 4,000. And going to have it in units is a good habit. We started with centimeters. We'll end with centimeters, but it's a cubic centimeters. 4,000 cubic centimeters. Nice. Well, that's today. But we'll do some more next time. So make sure you come back for the next session. All right. Bye.